Hello. This will be a demonstration of proposition 31 from book 6 of Euclid's Elements, which says that in right-angled triangles, the figure on the side subtending the right angle is equal to the sum of the figures on the sides containing the right angle. What this is going to look like is that we have some right-angled triangle, ABC, and we're going to say that the right angle is right here at BAC. So this angle BAC is a right angle. And we're going to have similar figures described on it. So the very simple case, let's just make these rectangles like that, and like that, such that all three of these rectangles are similar to each other. And what we're going to prove is that the figure on the side subtending the right angle, that is on BC, is equal to the sum of the similar figures on the remaining two sides. So the figure on BC is equal to the sum of the figures on BA and AC. We're going to begin by dropping down a perpendicular from the point A to the straight line BC at the point D. We can do this by 112. So AD is perpendicular to BC, which means by proposition 6.8 that we have three similar triangles formed here. So for example, the triangle ABD is similar to the whole triangle ABC. Again, that's prop 6.8. So the triangle ABC is similar to the triangle ABD, which means that the corresponding sides will be proportional, namely that CB is to BA, just as AB is to BD. But we have three straight lines proportional here, which means by the porism of 619, the first CB, so CB is to BA, just as BA is to BD, which means that the first CB is to the third BD, just as the figure on the first, which is CB, is to the figure on the second, which is BA. Again, that's the porism of proposition 619. And we can actually invert this proportion by the porism of 5.7 to say that the straight line BD is to the straight line BC, just as the figure on BA is to the similar figure on BC. Now we can prove in a similar way that CD is to BC, just as the figure on AC is similar to the figure on CB. This would be done just by noting that not only is ABD similar to the triangle ABC, but so too the triangle ADC is similar to the triangle ABC, which means you'll have three straight lines which are proportional, which means you can use the porism of 619 to say that CD is to BC, just as the figure on AC is to the figure on CB. Now, we've just shown that BD is to BC, just as the figure on BA is to the figure on BC, but CD is also to BC, just as the figure on AC is to the similar figure on CB, which means we have six magnitudes which satisfy the condition of proposition 524. We have a first, which is to a second, just as a third is to a fourth, and a fifth, which is to that same second, just as a sixth is to that same fourth, which means, again, by proposition 524, that the first plus the fifth is to the second, just as the third plus the sixth is to the fourth. In this case, that BD plus DC is to BC, just as the figures on BA and AC are to the similar figure on BC. But we can see that BD plus DC is just the whole of BC. So BD plus DC is equal to BC, which means also that the sum of the figures on BA and AC are equal, or is equal to, the similar figure described on BC. And this is exactly what we set out to prove. We set out to prove that the figure on BC, which subtends the right angle, is equal to the sum of the figures on the sides containing the right angle, namely BA and AC. And we have just proven that, which means we are done with the proposition, therefore, etc. QED. This is very obviously an extension of proposition 147, the famous Pythagorean theorem. That theorem, or that proposition, states that the square on the side subtending the right angle is equal to the sum of the squares on the sides containing the right angle. But this proposition, 631, extends 147 to include any similar figures. So obviously it includes the particular case of 147 since all squares are similar to each other, but you can have this with similar rectangles or similar triangles, or it's not even limited to rectilineal figures. You can do this with semicircles, for example, or other similar segments of circles. And this is something that the mathematician Hippocrates noted. Not a Hippocrates of Kos, who is the physician, but before him there was Hippocrates of Chios, who's a mathematician right after Pythagoras. And he is credited with discovering this figure called the lune. Now, what exactly is the lune? So it looks something like this. So let's say we have a right isosceles triangle, like this. Let me just make sure this actually looks good. So we have some right isosceles triangle, and we're going to call this ABC. And again, the angle at A is going to be the right angle. And we're going to reflect this about BC, so we're going to have another right isosceles triangle. We're going to call it BEC, and the angle at E will also be right. And we're going to bisect C at the point D right here, like that. And what we're going to do from here is we're going to describe a semicircle on BC with the center D. And you'll notice that this forms two similar segments on BA and AC. So this segment right here is similar to this segment right here. That's fairly easy to prove. I'm not going to go through it right now, but just know that this segment of a circle is similar to this segment of a circle. And we can also do this if we take the center E and distance EB or EC. All of these are equal. And if we describe a circle with this, this is actually just going to be a quarter circle though. It's going to look something like that. This segment of a circle right here is going to also be similar to these two segments right here, which means that this segment plus this segment equals this segment right here. Again, because they're all similar and this is a right angle triangle, it satisfies proposition 631. So this segment plus this segment equals this segment right here, which is on the hypotenuse, which means if we add this misshapen area right here, this thing right there, if we add it to both of them, well, if we add it to the larger segment, we'll just get the whole triangle. Because we notice that this black area here, plus this shaded segment, the one on the hypotenuse, makes up the whole triangle. But then it's also equal to the two similar segments on the legs of the right triangle, plus this weird black area. And we notice that we get this area that sort of looks like this. And this right here, this is called a lune. It's called a lune after the Latin word luna, which is the word for moon, because it looks like a moon. This figure right here, so this whole thing right here, if I'm actually just going to erase that out. This whole thing right here, this curved figure right here is exactly equal to the area of this right triangle. And what Hippocrates discovered was the first non-rectilineal figure to be entirely equal to a rectilineal figure. Namely that this lune right here contained by A, B, and C is equal to the right angle triangle A, B, C. And it's honestly really pretty. I really like lunes. They're a lot of fun to work with. So yeah, that's all I've got to say about this proposition. So I'll end the video here and move on to 632.